or 45. Alright, we are grading right now. I hope that we got grading. The grade should be out of grade for probably Monday or Tuesday. Hopefully, it's no problem. Usually, they usually problem. So, yeah, Monday or Tuesday. So, exam three, we have a free grade. Right? But they're not shot. Shot. All right. Okay. We're gonna move on. Okay. So we're on this chapter. So last time we have seen that the compound that reactive carbon and ketone. We gone over alcohol, ethanol, and amines. Okay. This is three. Today we go over one. Just a couple of few ones, and then previous reaction is going to over. And we have seen the reaction in different one. We have acidic condition, the basic condition, they have what happens. Right? First reaction to have hydration, adding water to alkaline ketone, you get a hydrated form. Next one, reaction to alcohol, acetal formation. We go through one alcohol, you get any acetal. Second alcohol, all the way to an acetal. We do this reaction for a protecting group, it is cyclic acetal. Cyclic acetal is stable under what condition? It's for acidic condition. Basic condition. If you want to remove it, add an acid. Analyze the removal of the cyclic acetal. Okay. Alright, so we have learned that alkyne and ketones can react with amines, depending on the amine. Primary amine give you imine, secondary amine give you enamine. These two reactions have what do you know about their mechanisms? They are almost identical except one step. The last step. The last step, if you're trying to get rid of the charge to become more stable, become neutral, right? Primary amine have that extra proton. You can move it, you can get a neutral compound. While secondary amine does not have that luxury, does not have that extra proton, so you have to go elsewhere. And that's going to be the elimination instead of deprotonation. Okay. The Wolff-Kishner reduction, you get the alkyne ketone reaction with hydrazine, you get hydrazole. From hydrazole, if you add a phase, keep reaction, nitrogen coming off, and everything just gone. Okay, this one similar to clinical reduction of milder as well, preferable in the organism. And last one, we stop right here. So we have thioacetal instead of alcohol, so we have thiol. You get thiol with sulfur, okay, and you get thioacetal. We use this guy also, very similar. So we use it in the protecting group. This protecting group is more superior than cyclic acetal in one sense. This functional group is stable in both acidic condition and basic condition. You can remove it easily. If you want to remove it, it's super simple. Add the mercury chloride. Mercury and sulfur precipitate. Okay, and you can make that precipitate out. You learn in the solubility rule in the Chem 1. Yeah, so that sulfur mercury. Right? You can also remove the whole group altogether by doing hydrogenation with radiation. You don't need to know what the radiation is. It's a type of activator. Yeah. Alright, we have seen this type of reaction, start with a ketone and the ketone is gone. There are three reactions you can do this. Number one, cleansing reduction, are you familiar with it? Okay, there's a first one you learn. We just learned the cyclic thioacetal. And then the last one we have the Kishner reduction, you have to go through hydrogen. Okay, so it's a three. Three more ketone now. Right? On the synthesis, we're doing next Monday, so we're gonna well, I'll review this. You get to pick and choose what you want to do. Okay. All right. Move on to another new reaction. Have you seen this reaction before? Yeah, right. Hydrogenation, alkene, right? So it could be now something like that. Is it unsaturated? It could be saturated molecule. Sodium borohydride, lithium aluminum hydride, these two are reducing agent like these two. Okay. They keep these two reagents will produce hydride. When I say hydride, do you know what it means? What's the difference between hydride and hydrogen atom? what does hydride have? The hydrogen atom doesn't have one charge. Oh, one charge, one extra electron. Right? So hydride has a negative charge. Actually, it's hydrogen is a negative charge. Right? So the mechanism goes like this. So just review. We have sodium borohydride is going to attack. We get an alkoxide. Chlorination with a solvent, methanol, water, ethanol, water with something soluble in. Right? Or source, get a product. Lithium, aluminum, and hydride. Just like the same way. Attack with hydride attack, you get an oxide. Chlorination, you get an alcohol. Okay. Now we have sodium borohydride, lithium aluminum hydride. Which one more powerful? Lithium aluminum hydride is much more powerful, too powerful that you have to separate from the quenching step. You cannot mix the two together, otherwise this guy there, the hydrogen, they will attack hydrogen or water. Okay, so you have to separate them. All right. Sodium borohydride doesn't bother. Methanol, water, any proton salt can be added together. Then the reaction between these two is really slow. Okay, so that's the lithium aluminum hydride and then sodium borohydride. Reaction that we had to show. Now, next one. Have you seen the reaction? Some old stuff. I just did some old stuff. Okay, so we have to bring out the reaction. How can we do right here? Aldehyde. If you add an alkyl magnesium bromide, alkyl attack, you get an alkyl group. Alkyl attack, you get an alkyl. This is the same as lithium aluminum hydride. Does that make sense to you all? Yeah, if you don't say it, it is supposed to be lithium aluminum hydride. Hydride attack, you get hydrogen. Hydride attack, you get hydrogen. Same thing. Exact same mechanism. So, when your reagent is as powerful as lithium aluminum hydride, you have to separate from the quenching step. Alright, look on the left side. So we have phenyl magnesium bromide for phenyl attack. Look at the mechanism. Okay, and then you quench acid, water, works. That's it. Okay, that's a Grignard reaction. Okay, how to make a Grignard reagent? This is a Grignard reagent. How do you make that? Well, really simple. You start with an alkyl halide. Okay, add magnesium ether. Now, ether, you might be familiar with diethyl ether. Some of you might be familiar with THF, tetrahydrofuran. Because we use it on the reaction step. Ether, in this case, for two purposes. Solvent, what's the other one? And the solvent for sure. What's the other purpose? A stabilizer. Okay, so yeah, it is really powerful. It's not stable basically. You have to stabilize it. You can look up how ether stabilizes the reaction. Anyway, alkyl halide at magnesium is either of your choice. You're going to get RMGX. That's the reagent. You can start with an alkyl chain, magnesium is ether. Right, so that carbon is a new profile. You can start with the phenyl ring, right? You get phenyl magnesium bromide, the phenyl, that carbon right there. That's a new profile. And allyl Grignard and vanillin Grignard works. Okay. While variety Grignard reagent and ginger Grignard, the person who invented this reaction, of course. Okay. All right, give me the product. Let's go. Have a pen and go. In A, what's the first reaction do? What is that? Do you see? Do you? Do you see this right here? Power formation. That's a protecting group, right? So you protect the ketone. That's the first thing. PCC, I think you know what PCC does, right? Okay, oxidation to alcohol. What do you get? Alcohol. You get alcohol. Okay, and the last one we have phenyl magnesium bromide, so phenyl attack, right? And you quench it. Now you add water, you add acid, also which remove the protected group too. Same thing. Quenching and remove the protected group removal could be the same thing. Yeah, the same reaction. The first step in B, what does this guy do? Protect, right? Protect group. We get ketone, we get aldehyde, right? Which one react first? Aldehyde react first. That's why I put it right here. If you do both, there's no point doing the rest. Yeah, I could be more clear like that one. People like that. You can imagine. You can't protect me, otherwise not. That's not to do. Alright, once the aldehyde is protected, add lithium aluminum hydride. So hydride attack, quench. Get an alcohol. Yeah. The last step is hydrogenation with grainy nickel. Remove the protecting group, but no, you don't get the piece of that. Everything is gone. This is like thermal reduction. Okay. I'm sure you get better after this weekend. So you know to start studies, different activities. Yeah. All right. Yeah. All right. Next reaction. I think you're familiar with this reaction too. Okay. This reaction is called hydrogen formation. Okay. The person who invented for his name is Arthur Aswell, Dr. Chemist. Sodium cyanide. Have you used sodium cyanide before? In what reaction did you use it before? SN2? Remember SN2? Yeah, sodium cyanide, we use it as SN2 reaction. Okay, but now sodium cyanide work as well as a good profile. Sodium cyanide was attacked and the product is called cyanohydrate with water, and cyanol. Okay. Cyanohydrate is synthetically useful. I'll show you why. Yeah, I'll show you why. I'll look at the mechanism for cyanide attack. Yeah, and then you have handling the mouth and acid chlorination. Like that. Real simple. Just like acetal formation, like hydration, or any reaction in this chapter, the product and the reactant are in equilibrium. Depends on what which side of the equilibrium favor. Small ketones, small aldehyde, attack it easy. The product is favored. If you have like total group, that's not a on both sides. Okay, more quickly here, ketone have less reactivity. All right, and I think some of you remember that alkyl ketone could be propyrrole. Well, this guy is propyrrole. Adding group that carbon is a chiral center. Okay. All right, I mentioned before that cyanohydrate is synthetically useful. When you got to functional group, there's a lot of things you can do on it. For example, you see this much more in the next chapter too. Add lithium aluminum hydride and then quench the cyano group turn to be an amine group. With the hydrolysis and heat, cyano group turn to be carboxylic acid. Next chapter is all carboxylic acid. We'll talk about how this reaction works. Yeah, right now it's the carbon user. Your mechanism combination. All right, now reaction on the excited on hydrogen. Question on here?
If I can explain it, but how does the water get rid of the oxygen?
Yes. From cyanohydride to amines
To the carboxylic acid?
to carboxylic acid in the next chapter. That's a long talk, that's like 5 minutes talk. Yes. Do you guys remember one oral reaction from Oracle 1? You have an alkene, you add water and hydrogen composition using borane.
Yeah.
Yeah. That reaction is invented by Herbert Brown from Purdue University. Nobel Prize in 1979. He was orbital 4. Okay. But this Nobel Prize is being shared between two people. Herbert Brown, one of them. The other one is the German chemist. His name is George Wittig. Yeah. George Wittig used orbital 4 for us. Right. Let's take a look how this reaction works. Okay. One thing to pronounce this reaction is W, but you say like V. It's Wittig reaction. What happened in German? I don't speak German. Okay. All right. Look at the overall reaction. Start with having a ketone. You add something happens. Look at the product. Get it now. It's an amazing reaction. You can't really make it alkene out of nowhere. From Oracle 1 to make an alkene, you need to do elimination. Remember that? You need a good living group. You need to add a living group for the multiple steps. Wittig reaction allows you to do it one step. That's one step reaction. Okay. Oh, let's take a look what happened. Okay. Start with aldehyde ketone. We add this type of species called an elid. Do not call it Eli. Okay. It's called elid. If we add elid, 2+2 cycloadation. You familiar with 4+2? Am I right? This order reaction, this one 2+2. We have 2 electrons here and then 2 electrons there. 2+2 cycloadation. You get octa-phosphate. You don't have to memorize the name. Okay. Octa-phosphate. From octa-phosphate, we break the ring. So retro of 2+2. What does retro mean? You go backwards. So make the ring, break the ring. Okay. Mechanism goes something like this. So start with this carbon attack carbon, oxygen attack phosphorus. I'm gonna repeat this 10 more times. You see, I'm gonna keep repeating this word. Carbon attack carbon, oxygen attack phosphorus. This is my third lecture. My third time. But you're gonna get it. Okay. Same thing on the right here. Carbon with carbon, oxygen phosphorus. You break the ring. We get double bond and then triphenyl phosphine oxide. Okay. This is this Wittig reaction can be used to extend the carbon chain, and not just extend the carbon chain, it leads to a double bond. You can do things on it, and you know all the reaction that you can do on double bond. This double bond is formed, and preparation in situ or in situ. Okay, it means that you have to make this first and use it right away. Not like when you have reagent, you can make it, isolate it, and keep it. Okay. It's not that stable. You make it, you gotta use it right away. We call preparation cycle or disease. Okay. Lastly, this reaction is spontaneous for forward. The driving force is PO double bond. PO double bond is exceptionally strong bond. You can look up the bond dissociation energy. Okay. Let's talk about how it works. So there are 2 things we have to talk about first: how to make this an elid, and then how this reaction works. Let's start with the elid. Yeah, just like when you have reaction, you start with alkyl halide, add triphenyl phosphine followed by a base. SN2 elimination. These are the simple 2 steps you learned before. Okay. Look, we start out with the methyl primary or secondary alkyl halide. Add triphenyl phosphine. Phosphorus is a good strong nucleophile. So from phosphorus attack, you get a phosphorus salt, look like that. Now let's look at the phosphorus salt. Okay. This salt, look at the alpha carbon. Do you know which one is alpha carbon? Okay. I want you to imagine alpha hydrogen. Okay, that's an alpha hydrogen. I think you remember that alpha hydrogen, like next to the ketone, it's a little acidic. If you add strong enough base can pull that electron away, that proton away. There will be protonation. Yeah, so we can do the same way. Use a strong enough way, sodium hydride, sodium sodamide, phenol lithium, like alkyl lithium basically. I'm gonna use inhibitor lithium like that. Then put that proton out. That's it's in the resonance structure with the proton solution. Yeah, it is a major group. So my point is, when you add carbonyl and inhibited lithium to an alkyl halide, that carbon turns to be a new nucleophilic carbon. Are you guys? Does it make sense to you all? That's what we're looking for. Okay, that carbon turns to be a nucleophilic carbon.
Why does, when you put a resonance, why doesn't it form one of the signature?
What's what?
For the resonance from sugar, why doesn't it form delta? That's the.
Over object. Okay. All right, we take step of that's easy. Move forward. Okay. So how does it work? Oh, one thing. This is an SN2 reaction, right? Do you all know the limitation of SN2 reaction? It doesn't work. Do not use tertiary carbon. That's no SN2. Okay. Secondly, that's the max you can go. I don't know what is yield. Maybe the reaction is slow and use not great. Method primary usually the good one. Okay, that's an SN2. All right, once we have the now we're going to add on to an aldehyde ketone. I'm going to take a benzaldehyde to this reaction. Okay, so who is that soon? Carbon attack carbon, oxygen attack carbon, cycle. You get oxygen. Okay, and then followed by retro 2+2, oxygen phosphorus, and then carbon form the other one. All right. Let's try predict the product. We have A and B. Can you predict the product? Carbon and carbon, oxygen and phosphorus. That's it. Don't have to draw the mechanism.
In future synthesis question, when we have to do the bitch reaction, will we have to put the steps to prepare the yield?
You should.
Okay.
If you know what to do, you keep going. Don't wait for me. If you are lost, you don't know what to do, answer my question. Okay? So we have the phosphonium salt. What does the first step do? And lithium is a base, right? Base abstract proton. What's the most acidic proton? The alpha proton. Okay, so the first step, right? Again, the question is an IQ draw mechanism. I'm gonna draw for you so you get an idea, right? The first step, put the alpha proton in. And you get did it inlet. Yeah, that's an inlet. From an inlet, we got a benzaldehyde. So who react with whom? Carbon to carbon, oxygen phosphorus to carbon to carbon. We get this first as an intermediate, and then again carbon, oxygen phosphorus. That product. Okay, so again, it doesn't actually draw mechanism. From here, you can go here right away. Basically, it's carbon and carbon, oxygen phosphorus. That's it. You get it now. Do another one. Please don't try to draw the mechanism. Please don't. Where's the try? Go to me. Give me the product, please. Okay. In B, right? Give me the product right away. So carbon attack carbon, oxygen phosphorus. That's the product. One thing I haven't told you yet, B or C. This one gives you all C. Yeah. Question on here before we talk about EC.
What is the 11?
What does 11 mean? Anyone can, 11 girl. Stretch it. If you go on the row 11, it's all stage 3. So if we bring this in, like 10 and 11, what number? How many series do our selectivity EC. Okay, look at it for reaction. I copy and paste from a textbook. The top two is the Vinnick reaction, top two Vinnick reaction give you all C. Okay, and the bottom two give you all C. How does this work? Let's take a look at the English. Alright? Everyone look at the English, the top two. If you keep writing, what? Yeah? Look at the English. This carbon is the new profile. That carbon is the new profile. You follow it? Okay. What are these two carbon bonds to? Another carbon. Does it make sense? I can bond to another regular carbon. Now, compare contrast. Look at it in the new profile. What are these two carbon bonds to? Electron withdrawal. Have you heard that term? Alright. The top one we call unstabilized unit, not stabilized except the bomb rust next to it. The bottom one, okay, the bottom one is a stabilized unit with the air game and electron withdrawal next to it, the bomb rust know each other, stabilized negative charge. Okay, you can drop the resonance structure. This is electron. Okay. Unstabilized unit selectively next C, stabilized unit selectively next E. Okay, that's bottom line. Now, if you check or go to in other two, this is what we have to memorize. But you take it with me, what do you think gonna happen? Let's talk about it. Yeah? Alright, put your pen down. The following quiz won't be on exam. Is it clear? Okay, all you have to do understand how this works. It's gonna be slightly complicated. It's more like a lot of watching, a lot of analyzing. Okay, I'm gonna ask you how this works, and you have to answer me. Okay, all right. So let's take a look at this reaction. Look at the unit. What type of unit is this? Stabilized or unstabilized? What type of unit? Unstabilized. This is carbon next to a regular carbon. You know, from this is unstabilized unit. You see. How does it work? Let's take a look. Okay. So I'm going to redraw the ketone and make a long next like that. There's a ketone around behind. Okay. So around ketone and aldehyde, there's a pair of hindrance. That's the electronic repulsion. Okay. Look at the elix. It is a long chain. If I draw the full structure, it's not even full structure again. As you don't have a hydrogen control hydrogen, but it's a big molecule. Okay. So if I draw like that, I'm not going to have enough space to explain anything. So I'm going to short it like that for now. Look at it like an umbrella. Alright. Now, what do you see? So in the structure of alien, that's 11. How many carbon? 1, 2, 3, 4, 5, 6, 7, 8. I propose this a fake layer hindrance on the L2 group. Okay. And also hindrance plus electronic repulsion. There's a bunch of high electrons on the benzene. Okay. Alright. This two will react. This will react. Who attack who again? Carbon, oxygen, phosphorus, right? So these two have to collide. Can they collide head to head like that? No, like this? No. What's wrong with it? Everything is like no. You can't collide like that. Too much electron repulsion. Okay, remember this is two triphenylphosphine, triphenyl free benzene ring order. Okay, so this one is work. Can they collide like that? Answer me one more time. Who attacks whom? Carbon, oxygen, phosphorus. How do they even react like that? You have to carbon has to form bond. Oxygen, phosphorus have to form bond. That doesn't work either. How do they collide? Yeah. Okay. All right. They are 4 ways. These two molecules can collide. But I don't have to go in 90 degree angle like that. All right. Now, which one leads to the most stable transition state? 1, 2, 1, 2, 3, 4. Which one looks the best? Let's do this. Let me ask you, what's wrong with 1? Good job. See, you can see this on your own, right? What's wrong with 2?
Second.
Yeah, so you can run alkyl group and the benzene ring. Yeah, now who is the best one? What's wrong with four? There it runs. It's a bunch of alkyl group like. Remember how many? You better go back. How many carbons on there? How many carbons on there? Go check. Yeah, I don't remember. Anyway, so this when these two collide like this, it will give you the best, the most stable transition state. Are you guys following? When a transition state was stable, what happened to activation energy? Low. When a low activation energy, what happened to the rate? Faster rate. This is the fastest reaction like that. Okay. All right. From here, watch. You're gonna get a C. Are you gonna see? Who attack who again? Carbon, oxygen, phosphorus. So let carbon attack carbon, oxygen attack phosphorus. I'm just gonna leave like that from a bond. Here we go. Of course, it look weird. It won't look like that, of course. All right. But now, give me the space or speed. You don't see it yet. Let me show you. The intermediate is oxide phosphate. It's a formula but like a square, right? This is a twisted square. I have to make it look like a regular square first. So this is what I'm gonna do. I'm gonna twist that bond, okay? Oxygen will replace the hydrogen, hydrogen replace alkyl group, and alkyl group replace oxygen. What do you think? That's the icon. Okay, this is the icon. Let me summarize for you, okay? How come? What control the stereochemistry? Why you can't see isomer? Take a look at the whole thing we go over. What actually control the stereochemistry of the product? So you can run through, and then this is the best one. Yeah? That controls the stereochemistry. Right? And then the rest is gonna be like where who attack, and then go to see. Okay. All right, let's compare the contrast. Okay, let's compare contrast. We got E. Stabilized here, give you E isomer. How we get E? Same rule. Now I same rule, so we get all this same thing. But now this elite is stabilized elite. Can you see that? This is stabilized elite. This turns to be electronic propulsion. Okay, let's see what happened. All right, how do these two react again? How do they collide? Let's go ahead and degree sideways, like that. 1, 2, 3, 4. We're gonna pick one. Let's do it. It's all comparison. Which one looks the best? For sure, it's not one, right? Number one, electronic propulsion. A bunch of electrons, a bunch of electrons. Yes, sir. Now, look at number two. What's wrong with two? Easy to see. Second rank. Okay. Number three. Second rank. Number four is the best one. Okay. How come? Let me explain. Okay. You be like, hey, there's a second rank right there. Right? Let me ask you this question. What is the hybridization of that carbon? SP. I'm going to be good at to get this wrong. SP. Okay. This is ester, right? Does carbon have double bond? And that's an sp2 carbon. That's an ester, an sp2 carbon. Okay. Sp2 carbon. What's the geometry? Calculate that. What is that? You can calculate that. That's how you go. If you want to see the way that much, seriously. But this guy's flat. But imagine like how that is flat. Okay, when it's flat, not a lot of the kilograms, or this is actually the best one. And the rest we have hydrogen in the next to the carbon phosphate group, so hydrogen is flat, small. Hydrogen and oxygen, no electron propulsion, that's the best one. Okay, all right, now let's put the negative to react. Okay, who attack whom again? Carbon to carbon, oxygen to phosphorus, right? So you're gonna get to like a twisted oxide phosphate like this. This is trans or E. If you don't see it, I'm gonna do it. Rotate that bond, okay? Oxygen, replace hydrogen go to R group go to oxygen. That's a trans. Or you guys. Yeah. If nothing on here makes sense to you, of course, about 5 to 10% of you, nothing here makes sense to you. Look at that. That's another option. Yeah. All right. Don't look at your hand now. Don't look at your hand now. Tell me. Answer this question. We're gonna make with the pheromone of some type of mode. Okay. So start with compound. Look at this elid. What type of elid is this? Stabilized elid. You have this from Northern group, right? Stabilized elid. Give you E or C? He's gonna give you E. You're gonna get E. See that? Move on to the next one. What type of elid is this? Obviously, it is unstabilized, right? Unstabilized, you see? Because you can see, that's the thing. Yeah. Reduction in lithium aluminum hydride you have about this, the molecule. That's how we look at incidences. Give me the product. Go ahead and go. Let's go. Give me a product. Look at the elid. What type of elid is this? Unstabilized elid. Do you guys agree this is unstabilized elid? Yeah, okay, unstabilized elid. So this carbon is the new normal file. Okay, carbon attack carbon, oxygen attack phosphorus. That's the product. All right. Most of the time, when I see students, a bunch of students do the Vedic reaction. Normally, draw the product with the C or E isomers, not the critical point. Okay. The common mistake is the number of carbons. How many carbons are there? Let's count. I'm not ignoring that method. Okay. So 1, 2, 3, 4, 5. 5 on the left side. 6, 7, 8, 9, 10. The product going to have 10 carbon too. I usually say 9 or 11. Can you imagine that though? Under pressure, under time constraint. So like either you subtract one carbon or have too many carbons. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Same carbon. All right. Okay. All right. That's how you predict the product. Now, in synthesis, you do it next week. Okay, in synthesis. When you see that one like this, of course, most of you, okay, will think about, hey, we have to do elimination, right? That's how we trade. We have to do elimination. Then we need a living group. We have to add a living group. But how do you do that? We have to go with the radical reactor. That's 4 steps. Vedic reaction allows you to do those 4 steps in one step. Did you guys hear what I just said? Okay, this is a name reaction. It's a shortcut, basically. Right? You can do those short those 4, 5 steps in one step. Okay. All right. To make Vedic, there are 2 things you have to do. Number 1, listen. When you make a Vedic, there are 2 things you have to do. Number 1 is make the elid. Number 2, take that elid, react it out and ketone. Okay, there are 2 things you have to do. Right? All right. Let's do it. To make this. You can look, you got 2 options, either ketone on the left side and the elid on the right side is carbon and not carbon. That's one way. Or you have aldehyde on the right side, that's an aldehyde part, that's an aldehyde, right? And then there's Vedic on the left side, elid fact. Okay? The question is, which one is more efficient? Right? Which one is more efficient? Let's take a look at the top one. We'll look at the top one first. How do you make that elid? You need pyruvate phosphate to SN2 on purple, whatever, to the liquid. Right, that is the necklace, SN2. They're out of bed, of course. If you want to get elite, okay, you need pyruvate phosphate SN2 attack on the carbon. And I think you know which way is better. The top one, the top one is more efficient. Chemical reaction. Okay, so faster SN2, the smaller the nucleus, the smaller the alkylizer, the faster, the more efficient SN2 reaction. So, all right. So in this case, make the primary carbon on to make it elite is better way. So we're gonna start right here. Take the propyl group with the bromine, chlorine, poison group, two little group, pick one. Okay. Add pyruvate phosphate, add a base of your choice. There are four that you can use. Okay. And you're gonna get elite. From elite, add an aldehyde ketone that you want, and that's the product. Two-step reaction versus 4, 5 steps reaction. Okay, this is a name reaction. When I say name reaction, it means that they got people's name. Usually, I got something special. Right. One more name reaction to it. You got one more name reaction. Okay, so then the last reaction in this chapter. Reaction 10, failure, vinegar, oxidation. Two people here, failure, vinegar. Okay. From aldehyde ketone, we add in peroxy acid. Okay. I think you guys know some peroxy acid, am I right? We have hydrogen peroxide, what else? We have one in juice a lot. SCBA, remember that? That's the peroxy acid. Okay. All right. So the mechanism for lighting. Do you have an arrow with me? Is that an arrow in the handout? Yeah. Right. Okay. Good. All right. Just watch. I'll have to draw another one. Okay. All right. The first step is chlorination, and then the conjugate base of the peroxy acid attack the carbonyl carbon, so you get the peroxy acid on aldehyde ketone. Like that. There's a proton transfer, nucleophilic attack. I think you guys can do this. This is not that difficult. Okay. Now, this section, this is the key step. It's a little bit difficult to see. Okay, I'm gonna go slow here. Are you guys ready? All right, stay with me. Okay, I'll stay with me. This step we call rearrangement step. We call it 1-2 shift. Something shift one spot over, basically. We call 1-2 shift. Okay, this is how it works. We'll take a lone pair of that oxygen from double bond. All right. When this happens, that carbon is going to be over octet. Are you guys following? Something got to leave, right? There's no leaving group. It is on that carbon. So this happens. We call rearrangement 1-2 shift. That alpha group shift to the red oxygen. This is the microscopic step. And then the whole thing has to leave. That's the leaving group. Okay. Basically, from double bond and alpha group shift. 1-2 shift to the next station. That one we like we got 1, 2, 3. That's one. Yeah. The irreversible step is the driving force, drive everything forward. So there's one for that. Oh, it's right. No. One. Okay. Anyway, okay. All right, from right here, what happens after? You look at that proton. That's a acidic proton. And that's a product. All right, your turn. Okay, let's draw the arrow. All you have to do is draw the arrow. Right, the first step. Okay, first step, chlorination on that object. Now let's go. Let's draw an arrow. Get your hands on it. Okay. Sorry. I can. Interesting. Getting was pretty healthy. All right, first step, coronation. Okay. Second step, nucleophilic attack. Okay. All right. Here's a key step. How do you draw it? You need 3 arrows. How do you draw? From level 1. Okay. So one of these two columns gonna move. Right? You pick one. They are symmetrical, so you pick one. Right. So I'll do on the right side closer. So this, take this column, move to the red oxygen. The red oxygen will turn to the over object. So something doesn't leave. This whole thing leaves. That is whole thing leaves. Go home and draw a few times at home until you see it. Remember the first rearrangement you learned? Right? Or ring expansion. Remember ring expansion? Take some time. If you draw a few times, this, you can see it. It's not that difficult. Yeah, take a look at this. All right, right here, this book where we draw it, so it looks better. Okay. And last one, you draw it. And that. So at the end, we got the oxygen in the ring. You make it ester. All right. Now, happen later. Okay. Here's how we use it. That's how we're gonna use it. Okay. Having an acetone, symmetrical ketone. This one, nothing interesting. Okay. So the intermediate look like that. You know, one of these carbon will migrate. You guys watch. What are this carbon gonna migrate? What if carbon on the right migrates? You get this product. If the carbon on the left migrates, you get the same product. See that? Nothing interesting. Now, if we start with a symmetrical ketone or even an aldehyde, who migrates matters here because we get different product. Take a look. If the methyl migrates, you get this product. If the phenyl migrates, you get this product. Yeah? The question is, which group migrates? Can you predict that? I have 4 experiments to show you. Let's see if it makes sense. Who migrates? Let's see if you can predict. Okay? All right. Here's a 4 experiment. Are you ready? Number 1. I have acetophenone. Okay? Methyl, phenyl. If phenyl migrates, you get this compound. If methyl migrates, you get this compound. So we're gonna run this reaction, separate them by the chromatography, and then check the percent yield. Have you checked percent yield before in the lab? Yeah, very simple. Okay, check the percent yield. Percent yield goes like this. Who's the major product? Sorry, who migrates? Phenyl ring. Benzene ring migrates. Okay, so when we have phenyl, benzene versus methyl, benzene migrates. Next one, primary. This is methyl, this is primary carbon versus benzene ring. Okay, if benzene migrates, you get this product. If the ethyl migrates, you get that product. Anyway, yeah. Anyway, one reaction separate by column chromatography, and then check the percent yield. Who migrates better? Still phenyl ring. A benzene ring still migrate better. Next one, number 3. Secondary carbon and a phenyl ring. Okay. This is the product, possible product. Right? Phenyl migrate, as secondary carbon migrate. Who migrates better? Secondary better. Yeah. Yeah. What compound do I run? The last one. You see the step there. You see the pattern there. That's the cheery. That's the have the cheery carbon versus the benzene ring. Okay. Who migrates better? So here we're better. So we come up with we call migratory aptitude. Who can migrates the best? Okay. I have two hydrogen, so we have hydrogen. So here is the best one, followed by secondary benzene, primary, and then methyl. Methyl that doesn't migrate. That's how we do experiment. Okay, we have to run this experiment and give you a hypothesis or conclusion. That's the conclusion. How does it work? I'll let you know on Monday.